Welcome to Chapter Pi, which is all about limits. Most courses in differential calculus begin with limits. I like to end with limits. And now might be a good time to go back and reread some of the very beginning of the book, namely pages 3 through 6, in which I talk a little bit about the history of the subject and the role that infinitesimals and limits play. But in this lecture, the time has come at last to discuss the intuitive idea of a limit, and more specifically, how to rephrase the idea of a derivative in terms of limits without any specific mention of infinitesimals at all. Let's begin with a rough definition. This expression right here, which we read as the limit of f of x as x approaches a, this expression is the value that f of x approaches as x approaches a. Now, as I said before, this is a very rough definition. It can be refined considerably. But on a first pass, this should suffice to give you an idea of what limits are all about. And note that I have underlined these approaches right here. A limit as x approaches a is not about what happens when x is equal to a. It's about what happens to this thing as x approaches a. It's a subtle difference, but an important one, and I think I can make it clear with a picture. And here is the picture. I've got a graph of some function f, which appears to be defined for all real numbers except for 2. It's a curious sort of function, as it looks very different on different parts of its domain. For negative values of x, f of x always appears to be positive, but decreasing until it hits 0 when x actually is 0. Then, on the interval 0 to 2, exclusive of those endpoints, the function's graph looks sort of like the graph of the tangent function, with vertical asymptotes on both sides. At 2, the function isn't defined at all, and then for values of the input greater than 2, we have an initial vertical asymptote, and the function, for the most part, follows this weird behavior getting closer and closer to 2, except at this one spot, 3, where there's a hole in the graph, and the value of the function at 3 is 1, where we might actually expect it to have been 2. Alright, it's a goofy function just here to help us understand this idea of a limit. So let's look at some examples. First, let's look at the limit of f of x as x approaches 1. What intuitively does that mean? Well, that would be the value that f of x, the function's output, approaches as x approaches 1. So we're imagining if we take values of x closer and closer to 1 on either side of 1, what value will f of x approach? Well, it's pretty obvious in this case. If I'm approaching 1, say, from the right, then the value of f of x is getting smaller and smaller and smaller, and it's closing in on 1. That's the value it's getting closer and closer to. If I'm approaching 1 from the left, similar story. The value of f of x is getting larger and larger and larger, and it's approaching the value of 1. It's approaching 1 from above in this direction and approaching 1 from below in the other direction, but as x approaches 1, f of x, the output of the function, is also approaching 1. So we would say that the limit of f of x as x approaches 1 is going to be 1. We'll do several other examples to reinforce the idea. But I should mention in passing that as we came up with this limit, we were thinking about what happened as we approached 1 from the right and as we approached 1 from the left. And in both cases, f of x was approaching the same value, namely 1. There are instances in which we are only interested in, say, the approach from the right or the approach from the left. And there's a special notation that you see in those instances. And I'll write it down here so that you get a chance to see it right away. This thing I've written right here looks almost exactly like this thing. The only difference is this little plus sign. And what that means is that x is approaching 1 from the right. So we would read this as the limit of f of x as x approaches 1 from the right. And that means we're only interested in what happens to f of x as x approaches 1 from the right, as we go from 2 to 1.5 to 1.1 to 1.01 to 1.0001, etc., etc., etc. The approach in that direction. And of course, in this case, that limit is still 1. And I bet you can guess what the notation for approach from the left looks like. It would just be as x approaches 1 from the left with a little minus sign right there. So as x is approaching 1 from below, from the left, as we go from 0 to 0.5 to 0.9 to 0.999 to 0.999999999, etc. Never actually getting to 1, but approaching it from the left. And of course, as we approach it from the left, f of x is getting bigger and bigger and bigger and approaching 1. So that limit 2 is equal to 1. So things like this are called one-sided limits. And if both of the one-sided limits exist and are equal to one another, then we would say that the more typical two-sided limit exists, and its value is going to be the common value of the two one-sided limits. For the most part, we're interested in two-sided limits, but the one-sided ones do show up now and again. Okay, our second example will be the limit of f of x as x approaches 2. Now this one is a little different because this refers to the value that f of x, f's output, approaches as x approaches 2. Well, what happens as x, the input, gets closer and closer to 2? Well, if we approach 2 from the right, the output gets bigger and bigger and bigger and bigger. We have that asymptote right there. We would say that the value of f of x actually approaches infinity. And the same thing happens if we approach 2 from the left. The output gets bigger and bigger and bigger and actually approaches infinity because of that vertical asymptote. And so in a situation like that, we would just write that that limit is equal to infinity. Now, infinity, strictly speaking, is not a number, so this is a different kind of limit. But whenever you see that the limit of something is infinity, this is the idea. It's just telling you that as x approaches 2 in this case, the function's output is getting bigger and bigger and bigger without bound. Oh, and one other thing I would have you note about this example. This limit, the limit of f of x as x approaches 2, we can say is infinity, whereas f of 2 itself is undefined. 2 just is not in the function's domain. So sometimes, even if the function isn't defined at a point, we can still talk about the limit of the function at that point. Because once again, a limit is not about what happens at a point. It's all about what happens in an approach to a point. All right, let's move on to our third example. The limit of f of x as x approaches 3. This one also is designed to highlight the difference between what happens at 3 versus what happens in the approach to 3, which is what limits are about. So let's think about this. The limit of f as x approaches 3. That's the value that f of x approaches as x approaches 3. Well, if x, the function's input, is getting closer and closer to 3, what happens to its output? Well, its output is getting closer and closer and closer to 2. If I look at f of 3.000001 or something like that, the value of that thing is going to be very close to 2, just a bit under it. If I look at 2.9999999 or something like that, and stick that into the function f, the output of the function is again going to be very close to 2. It's going to be a little bit above 2. And the closer I approach 3 from either direction, without actually reaching it, the closer I approach 3, the closer the output will be to 2. So this limit is going to be equal to 2. Thus, the idea of the limit of f of x as x approaches 3 is very different from plain old f of 3, because f of 3 is just the output of the function f when we stick in 3. And if we stick in 3, the output is going to be 1, not 2. So f of 3 is 1, even though the limit of f as x approaches 3 is 2. And this discrepancy, of course, comes from this discontinuity in the function. It's sort of artificial, but it reinforces the notion of what a limit is all about, and that's why I gave it to you here. Okay, let's look at a fourth example, which I'm actually going to do in 3 subparts. Let's start with the limit of f of x as x approaches 0 from the left. Well, what's happening? As we take values of the input closer and closer to 0, but to the left of it, the output is getting closer and closer to 0 itself. So that is going to be 0. But suppose we had looked instead at the limit of f of x as x approaches 0 from the right. Well, that is a very different story, because then we would be taking values of x that are positive but very small. And the smaller they got, the closer they approached 0, what happens to the output of the function? Well, it's always going to be negative, and it will be getting more and more negative. We have a vertical asymptote here, so the size of those output values is growing without bound. And we would express that by writing that that limit of f as x approaches 0 from the right is negative infinity. Okay, so far so good. Now suppose we were to try to put these together into a two-sided limit and ask for the limit of f of x as x approaches 0 with no direction specified. Well, this expression would refer to the value that f of x, the output, approaches as x approaches 0 in any which way. But the problem is that the limit in this absolute sense just doesn't exist. Suppose the way I wanted to approach 0 was to hop back and forth, taking a value on the left of 0, then one on the right of 0, then one on the left, then one of the right, then on the left and the right. I can approach 0 that way by hopping back and forth and getting closer each time. If I were to do that, the output of this thing would not be getting closer and closer to something. It wouldn't be approaching anything, because half the time it would be getting closer and closer to 0, but the other half it would just be getting huger and huger negative numbers. So since this isn't approaching anything specific, we just have to say that this limit does not exist, and that's all there is to it. And it looks like there's one more limit I can talk about here. The limit of f of x as x approaches infinity. Now again, infinity is not a number, strictly speaking, but it's easy to understand what is meant by this. This is the limit of f of x as x is getting bigger and bigger and bigger and growing without bound. Well, in this case, we can see what that value is going to be. As we take larger and larger values of x, f of x, the output, is getting closer and closer to this value of 2. So we would just say that that limit is equal to 2. Easy enough. Well, I hope these examples give you a feel for the intuitive geometric sense of a limit. And now I want to move on and talk about limits in an algebraic way, where instead of giving you a function's graph, I give you a function's formula, and we ask for a limit. So let's do that. Now, let's look at some more examples. What's the limit of this function, 2x squared plus 3, as x approaches 4? Well, you could certainly think about the graph of this if you wanted to. It's going to be a parabola. But we really don't need to. We can just think about this in terms of arithmetic, in terms of algebra. We've got this expression here, and we want to know what its value approaches as its input approaches 4. And we can determine that just by thinking about the various pieces here. As x changes, this 2 doesn't change, this exponent doesn't change, this plus sign doesn't change, and this 3 doesn't change. The only thing that is changing is right here. And as x is approaching 4, what's happening to x squared? Well, obviously, x squared is approaching 16. If you square something just a tiny bit greater than or less than 4, you're going to get something just a tiny bit greater than or less than 16. So this piece goes to 16. Okay, so as x approaches 4, this approaches 16, which means that double of that approaches 32, and adding 3 onto that gives me 3 more, and this is just going to be 35, and that's all there is to it. Nothing deep. The ultimate effect was the same as if we had just substituted 4 in for x, but I want you to remember that we are thinking about this in terms of approach. Next example. Let's think about the limit of this function, 1 plus 3 to the minus x, as x approaches infinity. Never mind the 1 for now, that just sits there because it doesn't depend on x. But 3 to the minus x, what happens to that as x gets bigger and bigger and bigger? Well, we're looking at things like 3 to the negative 1,000,000th power, which is the same thing as 1 over 3 to the power of 1,000,000. Well, 3 to the power of 1,000,000 is obscenely huge, so 1 over 3 to the 1,000,000th power is tiny, 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 tiny. And the bigger x gets, this is not a million, but a billion and a trillion and a trillion trillions. This term is getting smaller and smaller and smaller. It is vanishing as x approaches infinity, which means that this whole expression is just getting closer and closer to 1, because no matter how big x is, the 1 just sits there, and we'll be adding 1 plus this thing, which looks more and more like 0 as we go. So that limit would simply be 1. Example 3. The limit of this rational function as x approaches 2. What's that going to be? As x approaches 2, what happens to the numerator? Well, this piece approaches 4, this piece approaches 2, and this piece just stays put at 1. So their sum is going to be 4 plus 2 plus 1, which is 7. What about downstairs? As x approaches 2, this term approaches 6, and the minus 1 just sits there. So the bottom is approaching 5, and that's that. And here you may be getting impatient and saying, yeah, I understand, you just stick in 2 for x. And in many cases, that will work, but not in all. Such as, in our next example, the limit of this rational function as x approaches 2. If you just rush to stick 2 in for x everywhere, you hit a real problem. You get 0 upstairs, but you also get 0 downstairs. And as you know, you cannot divide by 0. So you might be tempted to say that this is undefined, that the limit doesn't exist. You would, however, be wrong. If we clean this stuff up algebraically a bit first, we can see what's happening. So let's do that. The expression we are thinking about is equal to the limit as x approaches 2 of this stuff, because we had a difference of squares upstairs, which I have factored. Oh, and I want you to notice very carefully that this limit is written here a second time. A very common mistake for beginning students is to write the limit of something is equal to just that something in a different form without carrying the limit itself over. Be careful your equal signs actually are between equal things. Anyway, at this point, I think you can see what we can do. We have a common factor of x minus 2 on top and bottom, so we can eliminate them, rewriting this as the limit of x plus 2, which is all that survives the cancellation, as x approaches 2. And that limit, we can see at a glance, is going to be 4, because this approaches 2, and the 2, of course, just sits there and remains a 2. So even though, strictly speaking, this function that I have in the red box is undefined when x is equal to 2, the limit is actually defined and is equal to 4. This is a bit reminiscent of that geometric example where we had a hole in the graph. All right, next example. How about the limit of sine of x as x goes to infinity? Well, we saw an example earlier where we were looking at a limit as x went to infinity, and it had a very simple limit. What about in this case? Well, think about what happens. As you take larger and larger values of x, and you take their sign, what happens to the output? Do they get closer and closer to something? Do they approach something? And the answer, of course, is that they don't. Think about, for example, the graph of the sine function, the sine wave. As you take larger and larger inputs, the outputs just keep on bobbling back and forth between -1 and 1. They don't approach any particular value. That means that this limit does not exist. The output doesn't approach any particular value. All right, how about the limit of the logarithm function as x approaches 0 from the right? In fact, x has to approach 0 from the right because the logarithm function isn't defined for negative values of x. Anyway, what's this going to be? Probably the easiest way to think about this, as with this one, is geometrically. Think about the graph of the logarithm, which looks like this. Well, as x approaches 0 from the right, the logarithm goes to -infinity. So that limit is equal to -infinity. And I guess while we are at it, we might as well look at the limit of the logarithm of x as x goes to infinity. As we take larger and larger values of the input, what happens to the logarithm? Well, as you'll remember from your pre-calculus classes, the natural logarithm does go to infinity, but it really takes its time getting there. It grows slowly, but without bound. So if x is going to infinity, so is the logarithm function. The fact that its limit is infinite doesn't mean that it's getting there quickly. The logarithm function, after all, is the inverse function of the exponential function, and just as exponential growth is synonymous with extremely rapid growth, logarithmic growth is synonymous with extremely slow growth, but they're both going in the same direction. And as you can see, we tend to think about limits in a mixture of algebraic and geometric ways, by thinking about functions and their graphs, and the formulas that define functions, and so on and so forth. And I think we have finally reached the point at which we can talk about how to use limits to define derivatives without reference to infinitesimals, because that's where limits originally first came from. Those who felt uncomfortable with the notion of infinitesimals, which are a little weird philosophically, sought a way of defining what is meant by a derivative without having to think about dy and dx as actual infinitesimals. And the whole idea of a derivative can be recast in terms of limits very easily. And we'll turn to that next. Back in the beginning of this class, we discussed the idea of a derivative as a rate of change, a local rate of change, so that at any particular value of the input, like this, we could ask, at what rate is the function changing at that point? Not just what its value is, but what is its local rate of change, its local slope? And we said, well, locally, this curve looks like a straight line, the tangent to the curve at that point. And if we imagine zooming in on an infinitesimal scale and blowing up what we see on that scale, we would see that the curve and the tangent are 1, which means that local rate of change, that local slope, can be defined by the slope of this straight line, which is the same as the curve on an infinitesimal scale. And we referred to the infinitesimal change in x as dx and the infinitesimal change in y as dy, so that the slope here could be called dy over dx. And of course, we went on to learn all the techniques for computing these things from particular functions, and by now you are all, hopefully, masters of those techniques. But if some skeptic, some atheist of infinitesimals, said, yes, but I don't buy this stuff about dy and dx being infinitesimals. What is this business about infinitesimals? I'm only comfortable with real numbers. If you can't define this stuff in terms of real numbers, I want nothing to do with it. How do we put that person's mind at ease? Well, we might ask them, are you okay with this intuitive idea of a limit, since it doesn't make any reference to infinitesimals? And if that person says, yeah, the limits are fine, we want to be able to say to that person, okay, I have a definition of a derivative for you that doesn't require you to accept infinitesimals. We're still going to use this notation dy over dx, but if you want, you can just think of it as one big package. You don't have to think about it as a ratio of infinitesimals. Will that do? And if the person says, yes, that will do, then we can answer this person. And to show you how it's done, I have cooked up another little GeoGebra demonstration for you, which will look nicer than anything I can draw with my electronic pen and paper. So I will pull that up for you post-haste. Okay, here I have the graph of some function and a point on it, p, and the tangent at that point, whose slope, of course, is going to be dy dx. But this is all addressed to our infinitesimal skeptic, so we're going to say, don't worry, you don't have to think of dy and dx as infinitesimals. This is just notation. Think of it as one block where you can't divide up the dy dx, and we're only using that for historical reasons. We want to define what this thing means using limits so that we don't have to actually mention dy and dx as separate beings. How are we going to do it? Well, we are effectively trying to find a way to compute the slope of that tangent line without referring to infinitesimals. Our skeptic is perfectly happy computing the slope of a line passing through 2 points on the curve, because that's just the kind of thing you do in Algebra 1. You find the change in y and the change in x, make the ratio, and that's the slope. So let's go ahead and put a second point on the curve and the line that passes through it and p, like this. I call that second point v because I want to think about it as a variable point. I can take this point and move it around a little bit. No matter where we have it, it has some definite pair of coordinates, and p has some definite pair of coordinates. And we could find the change in the x-coordinates and the change in the y-coordinates between those 2 points, and of course we could call those delta x and delta y. These are perfectly real numbers, no infinitesimals involved. These are just small real numbers. And the slope of the blue line, that line that cuts through the graph as opposed to being tangent to it, is just delta y over delta x. Surely our skeptic of infinitesimals will be happy to admit as much. Okay, well suppose I let my point vary a bit. As it changes, delta x changes and delta y changes. But the thing to notice is that as v approaches point p, or in other words, as delta x, as the change in x-coordinate between the 2 points, approaches 0, what's happening to the slope of the blue line? Well, the slope of the blue line is getting closer and closer to the slope of the red line, because the blue line itself is approaching the red line. And in fact, if delta x is sufficiently small, still a real number, but small, we can see that dy dx, the slope we're trying to compute, is approximately equal to delta y over delta x, provided that delta x is a small real number. So far, so uncontroversial, because everything on the right-hand side of this approximately equal sign refers to real numbers. It's a ratio of 2 small real numbers. And now is where we will bring in the idea of a limit, because as we move this variable point along, as we let delta x change its value and get closer and closer and closer to 0, I can't actually let it be 0, because then I wouldn't be able to compute delta y over delta x, because I would just get 0 over 0, which is undefined. But as delta x approaches 0, we can say that in the limit, delta y over delta x is going to become the slope that we seek. And therefore, we can define the slope that we seek. We can define the derivative as a limit. Namely, we can say that dy dx is equal to delta y over delta x in the limit as delta x goes to 0. Everything on the right-hand side of the equal sign is something our skeptic is comfortable with. Delta y and delta x are perfectly good real numbers, no mention of infinitesimals, and he's already said he's happy to accept limits. So once again, we have our variable point, and as delta x goes to 0, this blue cutting line approaches the red tangent line, and therefore the slope of the blue cutting line approaches the slope of the red tangent line. And we say that in the limit, they are equal. And that's it. The stuff in that green box is the limit-based definition of a derivative. Now, this is also a place where you can imagine our skeptic saying, okay, I'm all right with the intuitive idea, but I feel like you've swept something under the rug, and you're going to have to give me a more careful, rigorous definition of what you mean by a limit, rather than just this intuitive notion of approach. And there's an answer for him there too, but it's more sophisticated than anything we need in a first calculus course. If you're interested in such things, you should take a course called Real Analysis, which concerns the deeper theory of calculus. It can all be done very carefully without any references to infinitesimals whatsoever. But this picture of the cutting line getting closer and closer and closer to the tangent line is the one you should have in your mind whenever you think of this limit-based definition of the derivative. All right, let's go back to the electronic blackboard, and I will show you how you can actually use that limit-based definition of the derivative to compute a derivative. And I will contrast it with how we computed one using infinitesimals back in the very beginning of this class. And you can decide which one you like better. All right, we are back in business, and let me record what we have just learned on our little GeoGebra adventure. The limit definition of the derivative runs as follows. To find dy dx, the derivative, we start with delta y over delta x, where these are small real values, and take the limit as delta x goes to 0. When we do that, we find that the result is the derivative we seek. Or rather, we define that derivative to be this limit. Let's turn to an example to see how this works in action. If y is x squared, if we look at the squaring function, we want to use the limit definition of the derivative to find dy dx. Now look, we already know what the derivative is going to be. We know it's going to be 2x. We proved that long ago. But we're doing it here without any appeal to infinitesimals, just using this limit definition so that we can stay safely in the realms of the real number system. Okay, here's our solution. By definition, we know that dy dx is the limit of this ratio of delta y over delta x, which is sometimes called the difference quotient, as delta x goes to 0. It may help to think about what's going on geometrically once again. We have our graph of the squaring function, and at any value x, we want to come up with the derivative, which will measure the slope of the tangent there. I'll draw the tangent in so we know what we're aiming at. But we're not thinking infinitesimally, for once. We're thinking in terms of limits, confining ourselves to real numbers. So how do we do that? We imagine a second point, and now we imagine not this tangent line, but the cutting line that passes through these points. We can think of the blue cutting line as a rough approximation to the red tangent line, a really lousy one in this case, but we know that if we take the point closer and closer, we'll get better and better approximations. And in the limit, this ratio will actually be the derivative we seek. On this picture, as I look at my 2 points through which the cutting line passes, I have my delta x, my change in x, and my delta y, my change in y. I'm just trying to remind you of what these symbols are actually referring to geometrically. The idea is that from x, we nudge everything forward a tiny little bit, delta x. We get a corresponding change in y, delta y. We compute the ratio of delta y to delta x, which gives us our approximation to the derivative, and then we take the limit as delta x goes to 0 to get the derivative itself. Let's move on to the next step here algebraically. This limit I can rewrite by expanding the top. It's going to be equal to what we had before, but with some changes upstairs. I want to write delta y in terms of x and delta x. So what is this delta y down here? Well, it's a change in y. It's the value of y after the change minus the value of y before the change. And let's think about those two values. The change was in moving from x over to x plus delta x. Now we've said delta y is the value of y after the change minus the value of y before the change. And y is the squaring function. It's the square of whatever we put into it. So the value of y after the change, well, that's the square of x plus delta x. So this should be x plus delta x squared minus the value of y before the change. Well, before the change, the input was just x. So the value of y was just the square of x. So minus x squared. If you understood that step, bridging that equal sign, then you're in great shape because the rest is purely mechanical. Let's continue onwards. As you might guess, we're going to expand this stuff algebraically so that all this stuff becomes the limit as delta x goes to 0. Don't forget to keep bringing that down until we actually take the limit at the end. the limit as delta x goes to 0, of this stuff gets expanded out into this stuff, just by ordinary algebra. The minus x squared comes on down, as does the denominator. And continuing on our algebraic endeavor, we see we're going to get some cancellation, because we have a plus x squared here and a minus x squared there. So getting rid of those leaves us with 2x delta x plus delta x squared upstairs. And we immediately see that we have more cancellation, because I've got a factor of delta x upstairs and a factor downstairs too. So dividing the top through by delta x, we get the limit as delta x goes to 0 of 2x plus only one of these two factors of delta x. And once again, observe that I am writing these limits down each time. Leave one out, and you have written something that is incorrect. But I have finally reached the point at which I can actually take this limit. Note what would have happened if I had tried to actually take the limit, like those algebraic examples we used earlier, all the way back here. We would have said, well, delta x is going to 0, so this piece becomes just x squared, and so I'd get x squared minus x squared on top, that's 0, and downstairs, this is going to 0, so I'd have 0 over 0. Well, that's undefined, so there wouldn't be anything I could do. It was only after doing these extra algebraic contortions, kind of like that example where we canceled out the factor of x minus 2 on top and bottom, that we finally put this into a situation in which we can take the limit. And now this is easy. What is this limit? Well, as delta x goes to 0, nothing happens to x itself, it just sits there like the 2, so this piece doesn't change, but this piece, of course, vanishes. Consequently, the limit of this expression as delta x goes to 0 is just going to be 2x, precisely as we knew it would be. If y is the squaring function, then its derivative is, of course, 2x. And we have just demonstrated this using the limit definition of the derivative. No reference anywhere to infinitesimals. So if infinitesimals strike you as somehow logically suspect, this is the argument you want. You'll have some exercises where you do something similar with other functions, but the main thing to recognize is that it's, for the most part, a mechanical process. The derivative you're looking for is given by this limit of delta y over delta x, the limit of this so-called difference quotient. You can expand the top, writing it in terms of x, and then you'll have a limit entirely in terms of x and delta x. And if the function's not too complicated, you can do some algebra to simplify this expression to eventually get it to a point in which you can actually take the limit without being stuck with 0 over 0. 0 over 0 is at the heart of every derivative when viewed this way, because, of course, the very definition, as delta x goes to 0, of course delta y is going to 0 as well, so you end up with this 0 over 0 situation that there's not much you can do with. I'll have more to say about it in the next lecture, which will also be the last one for this course. But some algebra brings us to a case where we don't have 0 over 0, and we can actually take the limit and come up with something sensible. Okay, now by comparison with what we just did, I want to remind you of how we actually first found the derivative of the squaring function back in the beginning of class. So, using infinitesimals, let's find the derivative of the squaring function from first principles, pretending we don't know the power rule. I'll run through the solution quickly. The derivative of x squared we first found by tucking the x squared up into the numerator of the fraction, and then we expanded this top out because we were thinking of this as an infinitesimal change in x squared. And that, you will recall, was going to be the value of x squared after the change minus the value of x squared prior to the change. Well, the change is just the change from x to x plus an infinitesimal bit more, from x to x plus dx. So the value after the change was x plus dx squared. And the value before the change was, of course, x squared. Next, we expanded this binomial, and that, of course, gave us x squared plus 2x dx plus the square of dx. And I still have that minus x squared hanging off the end, and the dx downstairs. Now what happens? Plus x squared and minus x squared cancel out. And then, more interestingly, the square of dx, by one of our main rules of working with infinitesimals, vanishes. It's gone, because an infinitesimal bit of an infinitesimal bit, a higher order infinitesimal, can be treated as 0. That leaves us with just 2x dx over dx. The dx's cancel, and we're left with 2x, and we are done. It feels easier now than it did a couple of months ago, doesn't it? Which version you like better is largely a matter of style and perhaps philosophical temperament. and I will leave it to you to debate with your friends and enemies as to which approach is better, or more appropriate at least, for a first course in calculus. Let's do one more example of using this limit definition of a derivative to compute a derivative, just so you get the feel of it. If y is 3x squared minus x, we'll use the limit definition to find the derivative. Now again, in practice, obviously we would not go to the limit definition. We would just stare at it and say the derivative is 6x minus 1. I'm only posing this problem to give you another look at how this limit definition works, in the hopes that it will help you with the homework problems. Our solution. The derivative, by definition, is equal to the limit of the difference quotient as delta x goes to 0. Pulling most of this stuff down, we recognize that the numerator has to be expanded, the change in y. Well, that's y's value after the change minus y's value prior to the change. And the change is when we change the input from x up to x and a bit more, to x plus delta x. So the value of y after the change is what we get if we stick x plus delta x into this function. In other words, this stuff. I've just taken this function, and everywhere there was an x, I have changed it to x plus delta x. And from the value of y after the change, I have to subtract the value prior to the change, which is, of course, just 3x squared minus x. It's the value of this function when the input is x itself. Now we're going to have to do some algebra up there. Namely, we're going to need to expand this. To save space and minimize tedium, I'm going to expand this and then multiply by 3 all at once. So we'll get an x squared, but I have to multiply by a 3, giving me 3x squared. We'll get a 2x delta x, but that also has to be multiplied by 3. So that'll be a 6x delta x. And we get a delta x squared, but that has to be multiplied by 3, plus 3 delta x squared. Distributing the various negatives here, we get minus x minus delta x minus 3x squared plus x. We should get a lot of cancellation here, and we do. We have a 3x squared and a minus 3x squared. We have a minus x and a plus x. So what remains becomes 6x delta x plus 3 delta x squared minus delta x all over delta x. Well, I can factor a delta x out of the top and cancel it with this delta x on the bottom, leaving me with the limit as delta x goes to 0 of 6x plus 3 delta x minus 1. Good. This is a limit I can actually take without running into the undefined expression 0 over 0. As delta x goes to 0, the 6x just sits there, and the minus 1 just sits there, but the delta x vanishes, which means that 3 times delta x vanishes too. So when we take this limit, we're left with the 6x and the minus 1, and that is all. It's exactly as we knew it would be. The derivative of this function is, of course, 6x minus 1. And you will have your opportunity to do a few of these in the homework. Be sure to read the accompanying section and do the assigned problems, and you will be well on your way to understanding the intuitive idea of a limit. In the next video, we'll push it a little further and talk about some special cases of limits and one neat trick that allows you to find some limits where you might not otherwise be able to do so. So, that's enough, and I'll see you in the next video.